Hello everyone, welcome to our Connection Wednesdays. This is already our third series of this regular online live training, and it is dedicated for all of you who are interested in steel connection design and maybe in IDEA StatiCa software. As usually, we will present some interesting example of connection. You will see how our customers use this tool for their work, for the design of their steel connections, and what you can do with our software. This is already our third series, but don't be worried. You can join the webinar anytime. And we prepared for you another eight webinars. This is the first one, and the series will continue till May. We will meet each other every second Wednesday, and the webinar will last about 30 minutes. My name is Jana Kaděrová, and I'm product engineer at IDEA StatiCa, and together with my colleague Adam, we will show you today some nice example of steel connection. You can communicate with us via questions panel in the GoToWebinar tool. If you enter your question, we will try to answer them during the webinar, and if we have some time in the end, we can also answer the most interesting ones loudly. And what will you see today? So the first project, it will be the customer example, and you will see an example from Heathrow Airport, how the company used our tool to optimize their steel connections. And in the end of the webinar, we will have a look at the default length of members in IDEA StatiCa. And as I mentioned before, in the end, we'll also have maybe a little time for questions and answers. So, and now let me pass the presenter to my colleague Adam, who will present the first example.
And the colleague Adam greets you as well, and wish you a good start in the year 2018. I'll just switch to my part of presentation. So the project I would like to show you today, and we'll take a look on that and click it through, is about the Heathrow Airport. This is a service bridge on the airport that's already built and in service, and it was built by Mott MacDonald and designed by one office in UK. And they were struggling with designing the connections there because they had no tool how to check such a complex topology, and also they were struggling with some, let's say, forces, or the design based on forces from various load combinations. So then they used our tool, IDEA StatiCa Connection, and they found out that it perfectly fit to their workflow. And how did it help them to achieve such a success? First of all, they were able to check any topology, so they didn't have to stick to any, let's say, templates or whatever according to the code. So that opened a new, let's say, designing universe. What were they able to design? And the second part, or the second side of that, was that they were able to design the connections more in economical way. So now they didn't use the envelope forces from all the combinations, but rather checked the connection with all the combinations one by one, but just inside one calculations. And we'll take a look how does this work, this second feature. I will start with a already done project. I will open this. This is the project that we got from the design company. And it was basically designed like this. And then it was checked with one, let's say, super combination or the envelope or maximum forces from all the combinations. And then they checked that. And they successfully designed this connection. But okay, so we can see the result of the calculation. All is green, all's fine. But then they questions themselves: is there maybe any way how to do it more economically to save material, save the building time on site, and etc. And let's say we would like to get rid of these stiffening plates here. So the first phase would be that we would just delete them or turn them off. So I will do that and see what happens if I recalculate the joint with the envelope forces. Okay. So what we see is basically a design that would probably be much better than the previous one. But let's finish the calculations, and that would probably show us what we expect. As we can see that already during the calculation that there's some huge plastification. That's why it takes so long, and probably this joint won't fulfill the code check and will fail. Well, because we just basically delete a part of the joint, right? We deleted the stiffening plates. So yeah, as I said, yeah, the plates plastificated about 12% and so on. So, but what's the trick here? This is calculated based on envelope forces. And this is, let's say, the old style, how we could call it. But the better and the right way is to check the joint with all the combinations. So let's see, I have 3 combinations here, and I will now import them to IDEA StatiCa, to this model. I will clean the envelope forces combination, and I will import these 3. And this is just example. And out of these 3 and many more combinations, they took the envelope forces, right? This is the regular way how it used to be done. But now I imported those 3, and I will recalculate the joint and see what happens if we pass or not pass the check. And maybe in the meantime, I can show you on our web page, ideastatica.com, where you can find in the resource center more information about this project. we have a part called case studies, and here you can read some more information about the about this project and how IDEA StatiCa was used there. And we have many more here, and of course many more information inside the resource center. Let me see, this is still calculating. So I can show you one more thing maybe. This would be typically done, this new approach of using combinations instead of envelope forces. This would be typically done when you import a joint from some structure design for software, right? For example, we have in this resource center, we have listed all of them that are connected to IDEA StatiCa connection. And let's see, I will pick the SCIA engineer and show you about how it's done. This is a typical BIM workflow that you install the BIM link to IDEA StatiCa and SCIA, and then in SCIA you just select a joint, then you import it to IDEA StatiCa like this. And this is important here. This is the point that I'm talking about. You import all the combinations from the structure software, right? And you can see also the combination description as well. So then you just run the calculation, and at once it calculates all of them and shows you the result, which is the worst scenario of all the combination. And this is what I've done here. So we end up with this joint, much lighter, and still we pass the check because we use the let's say more clever approach, the right approach. So here I can just show you, I know the stresses and the mesh generated, all the information that you probably know already or that you can go through yourselves. Let's see where strain occurs. Okay, that's in this plate. So yeah, this is I think very important thing, and something that we have to as a engineers, that we have to a little bit change in the way of philosophy of how we do that. And now we have the tool where we can. So that's pretty good news. And just one more thing maybe. How could we actually model this joint? That's pretty easy. I started with the finished project, but I'll show you quickly. It's really easy to model such a joint. So I'll show you how you can do that. So I'll just start a new project and select some basic topology. And I will just model this quickly. So let's see, I'll change here cross-section. It was made of SHS 120 by 10. Correct the length. And then I have 6 members here. They all have the same cross-section assigned by default, this K60. And if I don't want to change each by each, a cross-section of them, I can simply change all of them by one click. So I go here and change the cross-section here. Do this like this, 100 by 8. Okay, and it changed all of them. Okay, so I'll just make them some longer. This is unfortunately a thing that you have to do really each by each to change the default length. Okay, geometry done. About the load effects, as I already showed you, just import and you get the combinations. If you import a joint from a structure software, you get all the combinations loaded already. So I'm doing this from scratch, so that's why. Now, how to finish design, or how to do the design. I will use some operations here. First, I will cut the members. So I'll start with this one, D3, and I will cut it by the main beam, which is CH. And let me make this a bit wider. I will use butt welds. And here I show you one more trick, and this is that I changed to perpendicular. That's better visible with the other members. So I'll show you that there. So now I'll just copy this operation and assign it to D1. And here I show you the trick. If I change here to perpendicular, it will change the plane of the cut of the member, right? So as you can see, this is now just by one click, I get the desired shape or desired cut. Okay, and now just copy for D2 to H1, H2, those are the horizontal members, H3. Okay, so I'm done with cutting, and now I'll continue with the gusset plate. So I will assign it to D3. It's related to CH, that's good. And I will make it wider and higher. Okay. This is just one side weld, so I can change that here to have both sides. And I will say I want this, if I switch here to transparent, we can see that this goes through the member D3 like this. And I would like to have it notched by a rectangle, which will just cut a rectangle hole in the gusset plate. Okay. And now I will just chamfer these two corners of the gusset plate to those D1 and D2 members. So I go to editor and I add the chamfer operation of 100 millimeters and assign it to the left upper corner, which is number 5, and right upper corner, which is number 8. Okay, good. So this is looking good. And now I just copy this and assign it to the horizontal members as well. So H1 and the gusset plate there. And then the last thing is to connect those diagonal members to the gusset plate. So I will use for that the cut operation. Oh, sorry, not cut, but the cut of plate, which is this one. And here I will say, I will start with the D1. So I will change to member. Member D1 part is the web one. And the thing here is, the trick is that I switch from cut to notch. Okay, so we can see it changed here. And we cut by gusset plate number 1, that's correct. And I'll just switch the fillet weld to the outside because now it was inside the tube. Let's see, like this, which is not really fine for deconstruction. So let's switch it to the outside. And if I switch to transparent view, I can see we have these notch or cut of plate and the member in the SHS profile. And now I just basically copy this operation and to all the walls of the SHSs. So this is web number 3, good to go. Now another copy, D2, web 3, good. Another copy, D2, web 1, good. And now continue with this, H3, so switch here. This is now web 2 and cut by gusset plate number 2. So there we are. Another copy, web 4 on the other side. And now for this member, which is H1, H2. So this side and the other side is web 2. Okay, and that's it. So in, I don't know, 5 minutes, we just designed this joint. And we are good to go to calculate and to get the result that I already showed you. So that was my part. And now I give presenter back to Jana, who's going to show you some part of the theory of the length of the members.
Okay, thank you, Adam. So now we'll have a short look at the default length of member in IDEA StatiCa. So sometimes people ask us, what does it mean if they see that the length of member is 0? And obviously it's not 0 in the model. So the 0 corresponds to some default length of member. And now I will show you how do we calculate the default length. So there are 2 different formulas, and the one is applied on the biggest member of the connection. So the length of the biggest member, it's 2 times some coefficient k and times the maximum size. What is the coefficient k? It's 1 for ended members and 2 for continuous members. And what is the maximum size? So the maximum size is the biggest size of the cross-section, but not only of this member, but of all members in the connection. So generally, it will be the biggest size of the biggest member. For other members, it's 3/4 of, again, of some coefficient 2, then the number k, and again the same maximum size. This number 2 can be changed in code setup. So by default, we calculate with twice, for example, the height of the biggest member, but you can also change it in the code setup. And now let's just show some examples. So for example, the connection that you see in the picture. So the maximum size is 140 millimeters, which is the height of the column C. So the length of the column will be 2 times 2 times 140 millimeters, which is 560 millimeters. And for the beam, it will be 3/4 times the number 2, which is given by the code setup, times 1, because it's ended member. And again, I will use these 140 millimeters as for the size of the as for the length of the column. So this is the default length, and it's also measured from the node. So it's not measured from the, for example, from the surface. If you see the member B, the length is given from the node till the end of the member. I want also to mention that this default length, it's not a rule that you have to use this number. Actually, this length is kind of compromise between some compromise for the model, because the length should be short, because if we make the length longer, we are extrapolating the internal forces out of the node. In IDEA StatiCa, we only input internal forces at the node. So if you make the members longer, you are losing a little bit the correctness. But at the same time, we need some length so that all the plates and all the parts of the connections can be placed. So you can, anytime you can change the default length if you need to. It's not a dogma, but please have in mind that you cannot model the length of all the beam. That's definitely not correct. So please stay in a short distance from the node. Okay, and maybe I didn't mention that you can change the default length in geometry. Maybe I can show you some example. Okay, so you can see that I can change the 0 length here in geometry. Yeah, so this is okay. So I think that's all that we wanted to present. There are several questions, and one was how to save other material in the library permanently. So that's something I want to show in the next webinar. Definitely we can store the information about the material. We use this library MPRL, and maybe next time, or maybe in 4 weeks, we will play with it a little bit so that you can find out how to use it correctly. Okay, Adam, do you have any other questions?
So you let our attendees intend to come in for the next webinar. It's a good strategy. I think I have nothing to add.
Okay, so then you will be asked to fill a short survey after the webinar, and the recording of the webinar will be available in I don't know, 2 or 1 day. It will be on our webpage or on our YouTube channel. And if you are interested in getting a trial version, please go to ideastatica.com and fill in the form for a trial version. You can also visit our resource center, which is a big library of any documentation for the software, and the next Connection Wednesday will be held on the 7th of February, and I think it will be held by our UK team, so you can really look forward to their their connections. They're always very nice. Okay, so that's all from us. Thank you very much for your attention, and we hope that we will meet again next time. Goodbye.
Definitely. Bye-bye. Have a nice day.